Okay, 6.6, vectors. Vectors. Use magnitude and direction to show the vectors. We're going to visualize scalar multiplication. In other words, is it getting longer? Addition, subtraction of vectors. Vectors in a rectangular coordinate. Um, perform operations with vectors in I and J. Find the unit vector, write vectors in terms of its magnitude and direction, and then we're going to apply it. This will take 2 or 3 days, or at least couple 2 or 3 lessons. Starting off with, you can see how you've got different forces going on. You've got gravity. You've got somebody leaning back against the wall. You've got their actual weight pushing down, right? The vector of leaning forward, or sliding forward possibly. When you put all those vectors together, over here you can see that there's some sort of balance. That's the idea. We're looking at how these vectors work on each other. All right. You have in a vector, you have a directed line segment is really what it is, with an initial point and a terminal point. Okay, so you got some vector. And usually vectors, we mark it with half an arrow like that. So PQ is a vector, not a line. The magnitude of the directed line segment, now the magnitude is a specific length. We represent this by the double absolute value marks. Represents distance or length of a vector. You can represent vectors as boldface V's or PQ or boldface any letters. Sometimes you're going to see it this way with the cursive letter. And then when we get down to it, in general, we know that vectors can be the same length and same direction. So in general, you're looking at vectors having a direction and a length. So clearly, these first two are equal. They are headed in the same direction. They have the same length. Here, they may have the same length. They may have the same magnitude, but they don't have the same direction. And the direction ultimately is going to be represented by an angle. These are opposite vectors. Notice that they're facing the opposite direction. They're the same length. And in this case here, it looks like we've got V is half of W or vice versa. But they're definitely headed in the same direction. So vectors, magnitude being length and direction, probably going to be some sort of an angle at some point in time here. Okay, so show that vectors U equals V, and all, they're trying to show you that, number one, do they have the same length? Okay, so if they have the same length starting here and going like this, right, you should be able to take that vector and map it onto this one, same length. The other thing that you're looking at is that it has the same direction. 3, well, I should probably do this as a rise of 4, a run of 3. And if you put those together, right, so they have the same direction and same angle. So in this case, what you're looking for is distance formula equals the square root of x2 minus x1 squared plus y2 minus y1 squared, and then slope, right? Slope of the first one is 4/3. Slope of the second one is 4/3. So they have the same direction. What about their magnitude? D1 is equal to, and you've got to take the square root of -2 minus a -5 is 3 squared plus 6 minus 2 is 4 squared. 9 plus 16 is 25 over 5. D2 is the square root of 5 minus 2 is 3 squared, plus 6 minus 2 is 4 squared, and you can see already that that's going to be the same answer. So not only can you visually see it, but you can see it arithmetically. And again, you've got half a vector, twice a vector, 3/2 of the negative vector. Notice that that one's facing a different direction. Multiplication or scalar multiplication means you have some number times some vector. The same direction of v when k is greater than 0. It's going to go the opposite if k is less than 0. In other words, 5 times v just makes this longer. Negative 5 times v makes it longer, but it changes the direction. All right, rectangular representation. This is what we're looking at when we're looking at adding vectors. Notice that I have u plus v. It gives me my resultant vector here. Now, how do you want to say that? It's the initial point, tip to end, right? And then the resultant vector is from the initial point to the end. Subtraction would work the same way, only you'd switch the direction of the arrows. Here it is. If I have v minus u, you're literally taking the length of v, here's v, and you're subtracting u. Now notice that u is this direction. Only now we want to take that and we want to flip it around so it's going that direction, right? And we want to put it tip to end so that my resultant vector is here to here. Okay? Tip to end. Tip to end. All right, we're going to introduce a arithmetic way of putting these things on a coordinate plane where we have a unit vector represented by I and on the x-axis and j on the y-axis. If you have 2i, it's going to be twice the length. 3i is going to be twice that length. And when you put those together, tip to end, you get a resultant vector out here, which happens to have a distance of the square root of 2, or a magnitude of I plus j. Okay, same representation. You've got AI plus BJ represented here. We would like those representations to be from 0, 0. They don't always come that way, and we're gonna figure that figure out how to represent that at some point. But typically we want a vector from 0, 0 to AB. The real numbers A and B are called scalar components of V. Scalar components of V. You got the horizontal and the vertical components where put them together and you have this thing called a linear combination. AI plus BJ. And again, remember the magnitude, right, is the square root of a squared plus b squared, or it's just a Pythagorean theorem again. A lot of information here, you guys. All right, so we want to sketch this, right? And we want to go 3i down 3j, and we have this representation from 0 to there. The magnitude here of v is equal to the square root of 3 squared plus negative 3 squared, or square root of 9 plus 9 is 18. That should be simplified into 3 square root of 2. All right. If you have 2 points that are not on where the initial point is not at the origin. Remember, we like vectors that start at the origin and then go from there. But what happens if they're not at the origin? What happens if this is out here? Okay. What you're going to have is you're going to have 2 points. Those 2 points are going to be represented here and here, point 1, point 2, and you literally can subtract those to find the vector that ultimately ends up back here. Okay, so there's a formula. Subtract the x's, subtract the y's. Probably should write the formulas down too at some point. Okay, so we've got 2 points. Point 1, point 2. We want to write it in terms of i's and j's. So v is equal to, and remember back here they said you're doing 2 minus 1, right? So it's going to be point 2 is 2i minus negative 1i, comma, 7j minus 3j gives me 3i, that should be a plus, not comma, plus 4j. And you'll notice I just included the i's with that. I guess the Blitzer, when he did that, he put the I outside the parentheses. You can do that too, but it's basically just a subtraction problem here.